So good morning, my colleagues, and I hope everyone is well. So I want to pick up here where we left off. We were talking about annuities, and I want to talk about growing cash flows. In this case, you're not putting in money the same amount constantly. The money is growing. So as it says here, we have considered only cash flow streams that have same cash flow every period. If, instead, the cash flows are expected to grow, okay, so let's highlight that because that's important. They're expected to grow at a constant rate in each period. We can also derive a simple formula for the present value of the future stream. So here's the timeline. So this is called a growing perpetuity. Okay. So it's a stream of cash flows that occur at regular intervals and grow at and this is the important words here, a constant rate. It grows at a constant rate forever. So a growing perpetuity with a first payment of 100 that grows at a rate of 3%. And here's the timeline, and you'll know the dots here. It's growing forever. So it's perpetually, right? So these are what the equations look like. Okay. So if we try to make an equation out of this, the present value of a growing perpetuity is, and this is the equation right here. It's not that bad, right? Here's the growth rate. G is the growth rate, and this is your regular interest rate. Okay. So suppose G is greater than or equal to R, then the cash flows grow even faster than they are discounted. Each term in the sum gets larger rather than smaller. In this case, the sum is infinite. What does an infinite present value mean? Remember that the present value is the do-it-yourself cost of creating the cash flows. An infinite present value means that no matter how much money you start with, it is impossible to sustain a growth rate of G forever and reproduce those cash flows on your own. So this is kind of important, right? Obviously, you can't keep growing it forever, right? Growing perpetuities of this sort cannot exist in practice. So this is going to be pink, right? You got to understand that, right? Because no one would be willing to offer one at a finite price. A promise to pay an amount that forever grew faster than the interest rate is also unlikely to be kept or believed by any savvy buyer. So that's really not going to work. The only viable growing perpetuities are those where the perpetual growth rate is less than the interest rate. Okay, so that's the only viable one. So that each successive term in the sum is less than the previous term, and the overall sum is finite. All right. Obviously, you can't make a infinite amount of money. So we're always going to assume the growth rate is less than the interest rate for this perpetuity. All right, so if you read down here a little bit, go down, and here's the timeline, and it comes down to a real nice simple formula. The present value of a growing perpetuity is that equation right there. Okay. Your cash flows, your interest rate minus your growth rate. Okay. So let's kind of highlight this a little bit here. And all right, so this is an important equation to understand. And it's almost like a perpetuity, right? Except for the addition of this G. So it's now the first cash flow divided by the difference between the interest rate and the growth rate. All right. So here's a nice example about endowing a growing perpetuity. And again, the math is so simple that Here was the previous example, but now it's going to grow. So you can see it's got a growth rate of 4% per year, right? So it's $750,000, right? If you include that growth rate right there. You see that? So because of the growth rate for this party, this whatever it is, this party, you've got to double the size of the gift. All right. All right. Let's watch this.
Endowing a growing perpetuity. Okay, so 3 examples ago, we endowed a graduation party to the tune of $30,000 a year. The problem is that there's likely to be inflation. So $30,000 today will not buy the same thing as it will in a couple years from now. So what we want to do is put enough money away so that the amount that we pay for the party can grow to account for the cost of inflation. Alright, so to do that, we first write down the cash flows we want on a timeline. We want $30,000 in the first year, and after that we want the amount to grow by 4% a year. Looking at the timeline, what we see is we have a growing perpetuity. So to figure out what the present value of a growing perpetuity is, what we need to do is go to the place in the book that has the formula for the present value of a growing perpetuity. Now, using this formula, we can solve the problem. The present value is the first cash flow divided by the discount rate minus the growth rate. So that is $30,000 divided by 8% minus 4%, which gives a value of $750,000.
All right, so it was that simple. Now let's talk about a growing annuity, right? A growing annuity. So a growing annuity is a stream of end growing cash flows paid at regular intervals, okay? It is a growing perpetuity that eventually comes to an end, okay? So this is the important point here. This is the important point. Eventually comes to an end. So the following timeline shows a growing annuity with initial cash flow C growing at a rate G every period until period N. So this has got a definite end. All right? It's got a definite end. All right? All right, so all things being equal, here is the equation for the present value of a growing annuity. Now, I think in Excel you might, I don't know if they have this equation. You might have to just do subtract off the growth rate yourself. I have to check and see if Microsoft Excel will have that. Okay. All right. So here's an example of a growing annuity. Here's the timeline. Right. And here's the calculation right here. 30 years. Right. Here's the growth rate, 5%. Here's the interest rate. Here's your 10% going in every year for 30 years. And you'll have basically $150,000 at the end of that year. All right, so let's go listen to this.
Okay, we're back with Ellen and figuring out how she's going to save for retirement. But this time we have an added complication. Because she knows her salary will increase, she knows she can put more each year into retirement. So what she plans to do is put $10,000 the first year and then let the $10,000 that she puts away grow by 5% until she reaches age 65. I'm going to solve this problem in precisely the same way as I solved Ellen's earlier problem. What I'm going to do is first compute the present value of all of Ellen's payments And once I have that, I'm going to compute the future value by compounding the present value 30 years. Let's start by putting the cash flows on a timeline. The first cash flow occurs a year from today when Ellen is 36, and that's $10,000. A year later, when Ellen is 37, the cash flow will be $10,000 growing at 5%. So $10,000 times 1.05. And that continues all the way until Ellen is 65, when the last cash flow is $10,000 growing for 29 years at 5%. There's something very important to notice about this timeline. Notice that in the 30th year, the final payment has only grown 29 years. That is, because the first payment does not grow, there are only 29 years of growth. Luckily, the growing annuity formula is derived exactly under this assumption. Let's go and see in the book. Notice how the last cash flow grows n-1 periods. With this in mind, we can now use the formula for the present value of a growing annuity to calculate the present value of all the future payments. Using the formula for the present value of the growing annuity, we can easily calculate the present value of the cash flows. Notice how the discount rate is 10% and the growth rate is 5%. And the number of years is 30 because, again, the growing annuity formula already takes into account that the first cash flow doesn't grow, so the last cash flow grows n-1 years. So the present value is about $150,000. To get the future value, we just compound this 30 years to get a value of about $2.6 million.
All right, so that was a good example. So let's. I want to get right to the equation for the growing annuity, and here it is. Now, this is if n is equal to infinity, so it simplifies it to the growing perpetuity, right? So the important point here is they said, what happens if it hits infinity? And so this is the growing perpetuity, right? Okay, so that's that. That's it for that. And let's see where we're going to go next. All right, I'll pick up here because I'm 13 minutes into this, and I want to make sure it doesn't get too long.